Hello and welcome to SimScale's webinar series. In this session, we'll be looking into an electric motor vibration analysis. Electric motors play a key role in various applications including machining, tooling, conveyor and material handling, and even in electric vehicles. In this session, we'll be looking beyond the motor efficiency and talk about a silent design killer, which is the structural resonance. Those who are new to SimScale, SimScale is a cloud-native simulation tool which allows users to simulate a variety of physics including flow, structural, thermal, and electromagnetics. We have a typical electric motor at hand to do a case study. And our objectives are twofold. The main objective is to test the rating of this motor and see if there is a safe space or a regime for the motor to operate. The secondary objective is also to push the limits of the motor by ramping up the RPM and checking the motor for a variable frequency drive capability. Here we have a motor which is rated at 1140 RPM and has a 6-pole configuration. The base motor frequency is at 60 Hz, and this is what we'll be testing initially. To do this, we can jump onto the SimScale platform and see what kind of results we can get from a motor vibration analysis, how to set up such simulations, and also additionally do the variable frequency drive analysis. At the end of this session, we'll be collecting all the results from the simulations, formulating a CAMPBELL diagram, and finding out the safe operating limits of the motor. Let's jump into the platform to see the initial or the key results and see how we can set up such a simulation using SimScale. For the demonstration purpose, we have only taken the shaft, the rotor components, and the rotor itself. We have run a frequency analysis using SimScale on this motor assembly, and now we are looking at the eigenmodes. Here we have an 1885 Hz first mode, and this is usually the breathing mode or the elliptical mode of any such motor analysis. You will see a widespread displacement all along the rotor and the other components of the motor. And although the displacement look pretty drastic at this intersection of the motor, if you run a harmonic analysis and find out the actual displacements, these displacements might be negligible. But still, this mode gives enough design insights to make sure you pick the right material properties, right design and shape of the motor. Let's take a look at how we can get to this point. With SimScale, any simulation starts with a 3D CAD geometry. SimScale is CAD agnostic, so you can use any CAD tool available in the market, and we do support native file formats including SolidWorks, Autodesk Inventor, Rhino, CATIA, and any other CAD tools available in the market. You can easily drag and drop a CAD geometry as a part or an assembly into SimScale into this dialog box. Once the geometry is uploaded into SimScale, you can then select or decide what kind of analysis you're going to do on this. As we already seen, you can do multiple analysis types, including the thermal for the cooling of the motor, the structural analysis, which we'll look into detail. You can also do electromagnetic analysis to find the forces and torque of the motor for the rated frequency. For this case, we don't need additional components like the fluid region because we're not looking into the pressure drop or the thermal side of the motor. You can easily edit a copy, delete the parts that are not relevant for your simulation. We have taken advantage of the symmetry here, and we have only the rotor case, shaft, and the rotor for our analysis. The next step is to choose the analysis type. You can choose the analysis type based on your requirements. For this particular study on vibration, we'll be using the frequency analysis, which gives us ultimately the eigenmodes of the motor at an operating range. Creating a simulation is rather easy with SimScale. SimScale provides you a simulation tree, which is a top-down approach where the users can give their inputs before starting the simulation. Let's take a look at the base case at which the motor is rated. In this case, we have three different materials assigned to the motor assembly: steel for the shaft, aluminum for the rotor case, and copper for the rotor itself. In order to define the actual conditions of the motor, we can set a few boundary conditions, including a fixed support, which is assigned to the slot of the shaft. We have two bearings on each side of the rotor itself, and we have the rated rotating velocity set to the rotor components. We also have an additional symmetry plane since we take advantage of the symmetry. Once when these conditions are given as input, you can directly start a simulation and let the simulation run on the cloud. You will get a rough estimation of the time the simulation might take and the incurring core hours. This covers the initial objective of the session here, to check whether the rotor or the motor assembly is operating at a safe range for the rated RPM. In order to verify whether the motor can run safely within the operating range and doesn't create any unnecessary vibrations or board loosening, we need to check the eigenmodes of the motor. This is written out as a direct output from the simulation as a table. You can see the listed out eigenmodes and their corresponding frequency, which can be downloaded for post-processing. This is exactly what we need to form the CAMPBELL diagram for this particular motor assembly. To extend this to the variable frequency drive objective, we would need to run this case similarly using different RPMs. The idea here is to ramp up the frequency and the RPM to see up until which point the motor can operate safely. This is relevant in cases where the motor is subjected to a variable frequency drive and the frequency changes during the operation. To do this, you can simply use the same simulation setup, duplicate the entire setup, and all you need to do is go into the rotating velocity condition, where instead of giving a constant RPM for the input, you can do a parametric input. Once the parametric input is set, you can directly start the simulation, which is going to run in parallel and give out the results of all the different RPMs that you have set. For a motor which is of a 6-pole configurations and a 48-slot rotor, the 24th or the 48th order of harmonic response corresponds to around 4000 Hertz. And if you look through the eigenmodes, you see that the second mode is close to 4000 Hertz, which means at 5000 RPM, this motor might reach the resonance. Let's take a look at how this mode looks like by animating it. The second eigenmode is at 4014 Hertz. And to make sure if this is a critical speed and that the resonance can happen, you can easily see that in visual feedback, these deformations are cornered or actually spread out to the end of the rotor shaft or the slot components, which almost creates a unnecessary vibration of the slots. And this might actually transfer to the housing of the motor, and the housing of the motor can actually operate as a speaker, amplifying these small vibrations. This is a critical challenge in electric motor design, which can be commonly referred as the whining of the motor at high frequency. In this case, we are also given out the eigen frequencies and the modes corresponding to the RPM that we have set for the simulation. And ultimately, to form a CAMPBELL diagram and find out the safe space or region within which the motor can operate, you would need to actually collect all these eigenmodes and frequencies for different RPMs, put them together in a CAMPBELL diagram. Here we have the CAMPBELL diagram of the simulation results, and to read this graph, you can see on the x-axis we have the different rotational speed in RPM, and on the y-axis we have the frequency in Hertz. For the first RPM or the base RPM case of 1140, we can directly see that we have different modes which are going and corresponding to 1x, 6x, 24x, and 48x order excitation. Especially for this case, since we have 48 slots, we'll be interested in the 48x excitation line, which is represented by the yellow dotted lines here. If you look at the first RPM, which is represented by the blue line, we still have a large gap between the first eigenmode and the operating and the excitation frequency. This is almost a 900 Hertz of gap, which is a good design criteria or a safety factor for the motor to operate without any unnecessary vibrations. To extend this, we actually ran the case with different RPMs, and we have plotted the eigenmodes for different RPMs as well in this same CAMPBELL diagram. One way to understand and find out the resonance is to actually see whether one of these order excitation lines crosses the eigenmodes. Around 5000 RPM and 4000 Hertz, we have an interference, which means there is a high chance of resonance and the frequency or the vibration will get amplified. While designing, we can consider that as the boundary of the motor, or if this is a high frequency motor application, you would need to actually skip this particular RPM and the frequency combination to make sure the motor's life is longer and doesn't go under any structural damage. That covers our session on electric motor vibration analysis, where we saw how we can set up such a simulation in SimScale, collect the results, and form a CAMPBELL diagram to find out the operating range for the rated RPM, and also test extended modes with different RPMs for the motor. Hopefully this gives you a good idea on analyzing a motor for vibration and finding out the safety regime for the operating conditions. Thank you, take care, and see you in the next one.